assuming that we cannot get closed loop solutions for the inverse kinematics, is that a way to approximate them with a numerical version? Because you're going to turn the inverse kinematics problem into a differential problem, into a discrete optimization problem. That's the idea. And that will allow us to control the robots in more interesting ways. So the objective is to use this to make a manipulator follow a predefined path, control the motion by being done to the manipulator, and apply the concept of differential motion to laparoscopic surgery. So we went through this problem several times, assuming that I'm controlling the robot using joysticks. Here, how can I make the robot follow the motion of the joysticks, assuming, for example, that the joysticks and the robot don't have the same degrees of freedom. I can't fully specify the pose of the robot from the joysticks if the joysticks has fewer degrees of freedom than the robot. So if I have many more degrees of freedom to control with 6 degrees of freedom in my hand, how do I handle that? That's one thing we can answer with the approaches we see here. Here is another option, another application is robot ultrasound imaging. So you see here the arm of the individual on that bench, and then we have a robot applying pressure with the ultrasound probe and scanning the tissue back and forth. So how can you control this such that there's always the same force being applied regardless of the position of the arm? So what are we doing? What question we are answering is this, in fact. If you want the robot to go from P1 to P2, how do we do that? We find the forward kinematics, then through the forward kinematics we calculate the inverse kinematics, and hopefully we'll find nice equations that will answer that question in a closed form. That's not always the case. What if we don't have the closed loop, the inverse kinematics? How can we make the robot go from P1 to P2 without knowing the inverse kinematics of the robot? And the answer is very simple. Let's create a function, and that function is the distance of the robot from P1 to P2. And now let's find the angles of the robot that will minimize that cost function, that will minimize that error. So we'll turn this into an optimization problem that is, but it doesn't use the inverse kinematics of the robot. We'll use the forward kinematics of the robot. So we're going to incrementally change these angles and watch how the end effector moves. And based on that trend, we'll find a way to then approximate the solution by slowly moving it towards P2. Right? So this is an optimization problem. What's the cost function? Is the error in position, the difference between the desired and the current end effector position. And what are the optimization variables? The angles of each joint. Right? So now you see it doesn't matter how many joints we have, how many degrees of freedom we want to control, we can simply turn this into a mathematical problem. So if you're dealing with now a cost function to be minimized, now let's look for mathematical ways to find the minimum of a function. Let's assume the first function there, y equals to x squared. What's the minimum of that function? 0, right? At x equals to 0, that's where the minimum occurs, and the minimum is 0. How do we find it? Oh, we simply take the derivative of the function with respect to x, equate that to 0, and solve for x. We get x equals to 0, we plug it back in, and you know that the minimum is 0, right? But interestingly, whenever we do this sort of problems, we don't care about what is the minimum. We want to know where the minimum is. So we are looking for where is the value of x, where the minimum is. So that's easy because that's a parabolic function. Now we cannot go any lower than 0. What about this function here? The x is squared, cosine of x minus x divided by 10. What's the minimum of that function? Depends, right? Now is it here? Is it here? Is it there? Is it here? Because all these points have a derivative of 0. Right? So now our method has no guarantee to work anymore because we can have what we call local minima, which are points here that are minimum of the function, but are not the global minimum of the function, right? Which in this case would be over there. Right? So we need better ways to find this. We could still attempt to take the derivative and equate that to 0 and work with that way, but we'll find multiple solutions and we won't know which one is the actual minimum of that function. So we need some sort of optimization methods. But what if the function we are dealing with is not single variable, has multiple variables, x, y, z, or theta 1, 2, 3, up to 6. Then instead of the derivative, we use the gradient. What's the gradient function?
Derivative of each variable.
Is the collection of partial derivatives of that function with respect to its variables. Right? And what does that represent? Well, that represents a field, a vector field that tells us in which way the function grows or gets smaller. So if you have a function f here of multiple variables, x in this case here is just a two variable function, x and y, the gradient is now a vector that has all the partial derivatives of that function. So the partial derivative with respect to x, with respect to y, and so on. When you take the gradient now is the collection of partial derivatives, which is also a function, right? Also a function, which means that that gradient can be evaluated anywhere on the plane of variables. Here we have x and y, so we can take x and y, take a point in x and y. Here we see the value of the function, so it's just basically the quadratic function here. We can take any point of this plane, plug that into the gradient, and the gradient gives us now a 2D vector. What does that 2D vector represent? Well, it represents now the way the function grows. For example, if we take a point here, minus 1, we'll plug in there, and we get a point here, a vector that starts at a minus 1, and it grows in that direction by that magnitude. What is that magnitude? That magnitude is the rate of change of the function at that point. All right. In this particular case here, it corresponds to the steepest ascent of the function. That's in that point, along that direction. That is the way we would find the highest change in the magnitude of the function. So the gradient is evaluated at any point and is a vector that points in the direction of the steepest ascent. Does that make sense?
So the steeper the function at that point is, the bigger the rate of change at that
yes.
point.
Yeah. Okay. Let's take an example here. Not just putting values on this function. Function that we are dealing with is x squared plus y squared. So there's this conic shape that shows a lot better in your pictures there. Here, for some reason, it doesn't, but it's a ball, right? A conical shape. So if we take the gradient, what's the gradient? It's the partial derivative with respect to x, which is 2x. The second line is the partial derivative with respect to y, 2y. Now we can take any point. For example, here, back here we have -1, -1. If we put it there, we get -2, -2. So the gradient at point -1, -1 is a vector that starts at -1, -1, and it has a magnitude of -2 this way, -2 that way, and points along that line. Right? Which means that along that line is the point of greatest ascent, which makes sense. Right? Because if we go along that line here, that's where the function goes up. Right? So if we keep traveling, that is this what it means. If we keep traveling on this plane in this direction, the function will grow at the highest possible rate. Yeah? Does that make sense? Any questions so far? Okay. If
It was flipped when the arrows just point towards the center.
it would be pointing towards the center. So the negative of the gradient would just flip the direction of all arrows, and then it would point in the direction of the steepest descent. Right? You can see it here in the middle. Here the arrows are pretty much zero because we are tending to a flat surface. All right. So what do we do with it? Well, we can use this to optimize to find the minimum of a given function. And the first algorithm we're going to look at is the gradient descent. But the idea is that we know now how the function evolves in time. We know how, if we travel in the variable plane, how the function increases or decreases. So we can use that to now always move along the line that provides the greatest descent. So if you want to start at any point on the variable plane, on the x and y plane, and find our way to the minimum point, what do? We follow the vector that it has the greatest descent, the negative of the gradient. So we'll follow a line along the negative gradient towards the minimum of the function. Right? If the gradient gives the steepest ascent, the negative of the gradient is the steepest descent. So that's equation 3. That's what it says. So when we start at point 1, x1, now x1 here is a vector of all possible variables that make up the function. We'll, x0, we're going to move by alpha along the line of steepest descent. What is alpha? It's a constant that you can choose. How much we want to move along that line of steepest descent is starting at x0. x0 is any point on the xy plane. Okay? And where is x1? Well, that's where we land. We start at x0. We are going to move by alpha along the line of steepest descent, and you're going to land at x1. What do we do next? Well, we evaluate the function, and if you're not happy, we'll move again, and again, and again, until we reach the minimum of that function. So that's the more generic way to do it. X plus 1 equals to x of n plus 1. Our next step is the current step minus the gradient of the function times the scalar factor alpha. Have you seen this before? Yeah?
In another class, just this semester.
This semester?
Yeah.
Oh,
Gradient descent.
okay, so I can go off programming or something.
Yeah. It's machine learning mode.
Okay, so you guys probably need a lot more machine learning. Alright. Hold on. Any questions here? Have you seen Newton props in optimization? Okay, we're going to see that. Yeah. I could have lied, I've never seen this before, but what they didn't ask a very tricky question. What's that? Yeah. Any other questions here? No? Okay. So, how do we actually do this? Let's get an example here. Let's go back to our parabolic function, x squared, and let's get our alpha to be 0.1. What's the gradient of this function? Always simply the derivative of x squared with respect to x, which is 2x. So we go back to our algorithm here. We're replacing the derivative, the gradient with 2x, and alpha with 0.25. Now we have to choose a starting point, and we're going to start at x equals to 1, which is up there. When x equals to 1, what's the result? What is the result? What's the next x? So if you take this side here, xn now is 1. That should be 2xn as well. What do you have? 1 minus 0.5, which gives xn plus 1 equals to 0.5. So we now go to iteration 2. So we have x2 equals to negative 0.5 times 0.5. 0.5 minus that, which leads us to x3, 0.025. And we repeat, and we repeat. And you can see that every time the iteration is getting, the jump that we see in iteration in the value of x is getting smaller and smaller, which means that we are converging towards a point where the variation here will be very, very small, indicating that we are really approaching the minimum of the function. What is the minimum of the function? Well, it's just these values here. What's the actual value of the function? It's this values here squared. Right? So they evaluate the actual minimum of the function. So you see here the first step was very big. We went from 1 all the way to 0.5. And then this step get smaller and smaller as we approach the actual minimum of the function.
What happens after?
After?
If we like keep going, like will that increase the rate of change? Like if we're gonna go up like that?
No, you see that this change is getting smaller.
Right.
It will continue to get smaller.
Okay, so it's not gonna shoot up. Right?
It will if you choose alpha wrong.
Okay.
Right? So let's see what happens. Let's go back to our example here. So our example here, you can see several problems with this approach. The first one is that depending on where we start, we'll end in different places. If we start over here, we'll likely end here. If we start over there, we'll likely end around here. Right? If we start over there, we'll end over there. So problem number one, the final solution depends on the initial guess, our starting point. Right? So this is case 1 and 2 here. The second problem is if we are moving out too much along the direction of theta's descent, we may make the system, the convergence is low, or we may lose convergence altogether. This is an example you can see there. I chose in that example lambda that is too big, and instead of now descending along here, I'm descending like that, jumping back and forth between the curves. This one we will still converge. We will just take a lot more iterations to reach the bottom. Right? This happens because the jump from the iteration is too big. Lambda is too big. So if you choose a lambda that is smaller, then if we start here, we would likely reach the bottom like that, not going back and forth. Right? So how do we find that value? I have to get to do trial and error. Okay. Another constraint is that the function must be differentiable. If the function is not differentiable, then this will not work. Okay, so it's one way we can do it, but it's probably not the best way because of these problems that we just observed. So let's see what we could do with it. Here, I want to approximate the sinusoidal function between -3 and 3 using a fifth order polynomial. So I can create a polynomial 5. This polynomial has 5 variables, a0, a1, 2, 3, and 5. And I want to find a 0, 1, 2, 3, and 5 that will make this polynomial look like a sinusoidal waveform, and it's only valid between -3 and +3. So how do we formulate an optimization problem for that? Well, first we need to define the error function. What's the error function? What was the difference between the two? I chose here to take the integral of the difference squared. You can do it the way you want, but that's one way. Basically, now comparing the area, integrating the error area between the two curves. The target, which is sine of the x, and the p of x, that is the one we are trying to calculate. That's the function. Now what's the gradient of that function? Well, it's the gradient of the derivative of partial derivatives of this integral with respect to what? What's the gradient calculated with respect to x. Right? X goes between -3 and 3. Right? It's a continuous axis, -3 to 3. What you are actually trying to find is the values of a. Those now become functions, variables, and we are solving for them. So you can now take the gradient of the function. Now this is a 5-dimensional problem, impossible to visualize the gradient. Right? But no, those gradients are the gradient is now the partial derivatives with respect to this case. Okay, so what's the optimization problem then? A vector now that has all a's is the one you're changing. So this is the initial, let's put it as the initial guess of a's, a column vector with all a's, the same structure of the optimization function, and on this side here we have the updated vector of all a's. Remember that this is also a 5 by 1, right? So this is a 5 by 1, this is a 5 by 1. So instead of x that we had before, now we have a1, a2, 3, 4, and 5. Same here, and there is the gradient of the entire function. And you can repeat the process several times until we are satisfied with the error that we get in equation 6, and then the values of this, the cells of this vector a are now the coefficients that we can use to make up the polynomial equation function. Does that make sense? The problem is identical to the one we had before, except that now we have more variables. And the cost function that we are minimizing is a bit different. Yeah? Sure? Okay. So there are some limitations to this. Let's take this one step ahead and look at the Newton-Raphson. So Newton-Raphson is another method, and this is the one we're going to stick with, but it's based on gradient descent. So we have to introduce gradient descent first. So the idea is a bit different. We have a curve, the blue line. We're going to find the minimum of this curve. So you're going to pick a random point as our initial guess. This initial point is xn here. So it's a function, clearly a function of x. We are picking that as our original point. So we'll now go to the curve, create a tangent line at that point on the curve, and see the intersection of the line with the x-axis over here. And then you go up and find our new guess. Another tangent line, find intersection, go up, our new guess. Another tangent line, intersection, and so on. Does that make sense? Let's do it one more time. So we want to find the minimum of the blue curve. We're going to start here. We're going to go up there and do the tangent line. What is the tangent? Does the tangent represent? The rate of change of that function. Right? So it would make sense to now travel along the direction of that tangent. And that's what we're going to do. We're going to go in the direction of that tangent, but where do we stop? Well, we'll extrapolate this tangent up to the intersection with the x-axis. Go up and intersect the curve. This is our new point. This is one iteration. Does that make more sense? And now we repeat the process. Now we are here. We take another tangent. We find the new intersection. We go up. We find the point in the curve. That's our second guess. And repeat the process. You see that every time we do this, we are moving less and less along the x-axis. The iterations are getting smaller and smaller in the same way that we did before. Yeah? Okay. So, what's the tangent? This tangent line here. This is basically the derivative is basically the slope of that at that point, right? So what's the slope? Well, it turns out to be this height divided by that distance, right? So this slope, which is the derivative of the function, is this is f minus 0 divided by xn minus xn minus plus 1. So if you rearrange this in the format we had before, in the format of having our next guess as a function of the previous guess, now our algorithm changed a little bit. We have xn plus 1 equals to xn minus the function divided by its own derivative. Yeah? Does that make sense? Mm-hmm. We have time to go over this one more time. No, we will see the stopping conditions later.
And this method, it solves for the limitations that we see in the rate.
Some of them. Some of them. So this is based on the same idea, except that a big part is different.
How does that make sense? So I do like x minus plus 1, sorry. So xn is there minus so the function of xn, which is the blue line, right?
Yes. So the function of
So how oh, okay, I see, I understand now.
this is f of x.
Yeah, makes sense, makes sense.
So this point here is f
You
of
just rearranged it, right?
yes.
Okay,
this
sorry,
is
okay,
Fn.
yeah, makes sense.
And this is f of x n plus 1. Okay. So now let's go back to our original problem here and see how this one applies. F of, let's give it the same equation, x or y is x squared, so the algorithm now becomes x minus 2 plus 1 equals to xn minus the function itself, xn squared divided by its derivative, which is 2 times x. So now iteration 1, we can start at a given point. Iteration 1, we start at 1. So x is 1, we get 1 minus 1 divided by 2, 0.5. So that leads us to this iteration. Now we go back, we place 0.5 minus 0.5 divided by 2, that, and so on. And you get the same that we had before.
I'm sorry. So here, like the f prime xn is the same as the f xn plus 1 and not.
Sorry, could you say that again?
So here we have the f prime xn. So this one is the same as the f xn plus 1 or not?
The same as the f xn plus 1.
Let's go back to the numbers.
Yeah.
So here you see this 2.1 is fxn, and one is fxn plus 1.
Mm-hmm.
So that one is the same as the f prime xn or not?
No, we have prime. Here is the derivative of the function. Okay, so this gives the same result, and for most cases will give a faster convergence than the gradient descent. Here I got a little unlucky because they're exactly the same, but this is supposed to be a bit faster. Okay. All right. So what do we do with all this? We can apply to now finally apply this to our problem of robot inverse kinematics. What's our what's our cost function if you're now dealing with a robot problem? It could be the Euclidean distance between 2 points in space. It could be the Euclidean distance plus an error in orientation, for example. We can make up this function. If you don't care about orientation, we can simply say that our cost function is a magic function of all thetas between between 2 points. How do you relate? How do we evaluate this cost function? Through the forward kinematics. We input values for thetas in the forward kinematics. You'll know where the function leads to. Right, so you can use the forward kinematics to evaluate the function. What's the gradient?
We also have to add the constraint of wrist, how we want to orient it.
We can. That would then be part of the cost function. Now the $1 million question, what's the gradient? Aha. Rate of change.
It's the velocity of
The rate of change, let's think about it, the rate of change of the end effector position with respect to the joint angles. I gave it a name, the Jacobian. Haha. That is the Jacobian. Right, so the Jacobian is right there. And then we're getting close to our solution. Let's consider now the robot having a forward kinematics equation K. So we input all thetas here in this function K, and you get the end effector position and orientation. Let's call XD the desired position of the end effector. So here we are only dealing with position. Let's forget about orientation for simplicity. So what's the cost function? Well, the cost function is assuming that this forward kinematics equation here gives us the position of the end effector as a function of the joint angles, we can simply subtract them. Right? And that's now our cost function that you have to minimize. What are the variables of this function? Theta 1 to theta n. As many thetas as we want. What's the gradient now? Well, the gradient is the partial derivatives of f with respect to thetas. What's the partial derivative of xd with respect to theta? 0. Right? Because xd is a point in space, right? It's a constant. So we are now left with the partial derivative of the forward kinematics with respect to the angles, which is the Jacobian of the manipulator. Right? So this term disappears, we are left with that. That's the gradient of f, which is exactly the Jacobian of the robot. Relating changes in the end effector position to changes in the joint position. If we were to now do the Newton-Raphson algorithm as a function of all these, how does the formulation of the Newton-Raphson algorithm changes? Just rearranging things here, I'm going to do rearrange in terms of the error function, cost function here. So I move this way, and then this guy moves to, move this back here, and then this one. Right. Just rearranging the function. So now if you look at this function, and you rewrite this as a function of the robot control problem, what changes? What is minus fxn?
So, negative inverse function of the original function.
That is the cost function,
Right.
right? So that is k of theta minus xd. What is this one? The next iteration minus the current iteration.
Sorry, it's not showing.
Well, that's simply the variation in the angles between two iterations, right? This theta k theta are theta n plus 1 minus,
We can't
Theta.
see if we're running it.
and then the last one is, the derivative of f is the gradient or the Jacobian. So this is what I have in equation 15 here, just rearranging that. Okay? Sorry, it's not updating. There. So, moving forward, we're going to make a small simplification here, and assuming you see here in equation 15, we have theta n plus 1 minus theta n. Isn't this the variation of theta between two iterations? I'm going to call that delta theta, which is something close to the speed of the angles, the joint angles. Right? It's a discretized version of the speed of the angles. It's a small variation in that. So if you solve for them, that's what we get. Delta theta equals to the inverse of the Jacobian, because I moved it over here, times the error desired minus the actual position. So you're attending to something very interesting. Let's look at again equation 16, very important. The variation in the angles is the inverse of the Jacobian times the error. The error is the desired position minus the current position of the unit vector. Alright, so delta theta can be seen as the velocity vector that causes motion of k towards x d. Let's represent this as a block diagram, maybe that will help. What's the input here? Input is the desired position. We subtract that. We're going to multiply this by that same lambda that we had before, just to speed up the process. Try to make the convergence faster or slower. Multiply that by, so here we must have k of theta. Alright, so xd minus k of theta times lambda times the inverse of the Jacobian. What's the result? Is delta theta. It's delta theta. Delta theta, so there's a small variation in theta. To go from the variation in theta to theta, what do we do? Integrate. So the other side of the integrator has theta. Now how do we go from theta to k? Well, that's the forward kinematics equation. So here we have k of theta. So what is this doing? This is a loop that will run several times, and the final one, once you decide to stop this, what's the result? The result is a set of angles theta that will minimize the distance between the actual position of the unit vector that is calculated from that theta and the desired position of the unit vector. So what is interesting about this is that we didn't use the inverse kinematics at all. So we let this run several times, and the result is the set of angles theta that minimize the transfer function. Sorry, the cost function. There is no guarantee that the error will be zero, right? But at least provides a valid solution that will approximate the end effector to that desired position.
So for this one and the equation, where is the lambda?
Lambda should be multiplied inward here. It's just to speed up the rate of change.
It's a scalar.
It's just a scalar, yes. So there's a small problem with this. What's the dimension of a Jacobian if you're dealing with a 3-dot planar arm? You want to calculate x and y position with it. Is a 3/2, isn't it? What's the inverse of a 3/2 matrix? Doesn't exist, right? The inverse exists for square matrices. So we have a little problem there. But luckily, there is what we call the pseudo-inverse, which is an approximated version of an inverse for non-square matrices. That's given in equation 17. Where this comes from, don't bother. Right? There's a lot. There's a lot here. But this is an approximation of the inverse. Problem number 1. Problem number 2. What happens if there is a singularity? This will blow to infinity at some point. So to avoid the singularity, we never want the Jacobian here to be, the determinant of the Jacobian to be 0. So to do that, we're going to add this term to the inverse, which is an identity matrix times a constant, a very small constant, just to prevent this from running into a singularity. So we'll always make sure that the determinant is never 0. So this mu here is a very small number, typically in the order of 10 to the power of -9, 8, something like that. Right. If you don't put it there, MATLAB will crash as you're running your optimization. So that's how we're going to solve this problem. So when do we stop? When do we know that we found a suitable solution? Well, we have several ways to do that. We can say run this a fixed number of times, let's say 100 times, and you take the solution that comes out of it, number 1. We can say that we want the error to be under a certain threshold, so we'll let it run until the error is below a certain threshold. Problem is, what if you never reach it? Right? What if the system is unstable, for example, or your condition is unstable, you're stuck there. You run it for a fixed amount of time, like 1 second, 2 seconds, or you can combine and say whichever happens first, and then you stop. Right? But there is no guarantee that this will actually converge to a solution. Let's do an example. Well, not an example. It's more like a heuristic example, and see how we would apply that to this. So we have this 3-dot robot arm. We know how to do the inverse kinematics of this, but let's assume that we don't. We're, for example, texting during lecture, and then we don't know how to do the inverse kinematics. Then we remember, oh, but there is the differential version of it, so better do that. That's fine. There are always other solutions. So what do we do? I'll define the inverse kinematics. Find the suitable values for θ1, θ2, and θ3 that will bring the end effector to a specific position without the inverse kinematics.
Let's read the transformation matrix.
First of all, find the transformation matrices. Right? Find the forward kinematics equation using the transformation matrices. In this is a 2-dot problem, assuming that we only want to control the x and y position of the end effector. The first thing to do is to find the forward kinematics equation and from the transformation matrix, and then get the x and y position from that. Right, so these will be analytical expressions that are functions of θ1, 2, and 3. Good up to this point? Yeah? Okay. Alright, so we can put these in now this vector x. And this vector x has the position, the current position of the end effector, the actual position of the end effector. It has here 2 functions. functions, one function for the x position and one function for the y position that is given from the transformation matrices. We concatenated that in vector x. So two expressions. First row, vector x is a big expression that it gives x. Second row is a big expression that it gives x as a function of theta 1, 2, and 3. Second, the Jacobian. What's the Jacobian of this manipulator? Is dx d theta 1. What else? Dx theta 2, dx theta 3, and dy theta 1, y theta 2, and y theta 3. How do we calculate the Jacobian? Well, we can analytically calculate it. Take the analytical derivative of the vector x, of x and y, right, and then plug it here. So this is not a numerical with fixed values. This is a function of theta 1, 2, and 3. Okay? Any questions so far? So here's the algorithm. So let's pay attention to this one. So let's start the algorithm by inputting in x the expressions for theta 1, 2, and for x and y as a function of theta 1, 2, and 3. We are going to give this a desired position. The desired position going vector xd and is x and y. We calculate the Jacobian. The Jacobian is simply the derivative of x with respect to theta. That's what we just did, right? And now we are going to give an initial guess to our angle. So we're going to put all the variables, theta 1, 2, and 3, in this big theta here, capital theta. And we're going to give it an initial guess, say 0, 0, 0. We assume that the robot goes from to 0, starts at 0, 0, 0. Now we're going to do a while loop. And this while loop is the error. We want the error, while the error is greater than a predefined error ed, we are going to iterate. What's the error? How do you define the error?
It's the difference between the position you want and the current position. of
The error is exactly xd minus x. So, when we enter the loop here, we're going to update x and the Jacobian with the values we had here. Input in there, we now calculate them. Calculate the error because when we know x, we know how far we are from the actual position, and then you can calculate the variation in theta that will bring the robot towards xd. That's the equation we had before. Lambda, a constant, the pseudo-inverse Jacobian, and the error. So this is an interesting control problem because the greater the error, the more variation we'll see in motion towards where we want to be. The closer you are, the smaller that will be. What is this? This is the speed. Right? How do we go from speed to position? Well, we can simply integrate it. And this will act as a pseudo-integrator. So I'm simply adding up the speed in every iteration. It's a bit more than that, right? I have to calculate the area in the data rectangle, right? Divided by the time, right? But here, time doesn't really mean, or the x-axis doesn't really mean anything. It could be fixed because we are controlling these steps through length. Right? So it's enough to simply add the value. So we take the original guess and we add theta to it. That becomes our new guess. We end the loop and go back to the beginning. We repeat with this new guess. And then we continue and continue until the error goes below a certain threshold. Does that make sense? So that's the algorithm we need to know. It's really important for lab 7 and 8. Once the loop is done, what's the output?
It's the rotation matrix.
Well, it's that is the values of theta, the last values of theta that we can now input in the forward kinematics to get the rotation and the transformation. Alright, and this gives then the final thing. So I posted this, implemented in MATLAB, I posted this code on Brightspace. Take a look at it and see if you can identify which portions of this pseudocode are where they are and how you implement it. It's really important. You have to implement this yourself for labs 7 and 8. Any questions about this pseudocode?
What is T1 for?
T1?
T1 for T2 for?
Right at the top. First.
Yes, those are we are extracting x and y from the homogeneous transformations.
Is that solution? Is the big one or it could be others?
Sorry, you had that.
I mean, it could be the other position, or it has to be like the 4x, it has to be 1, 4, and 2, 4.
Here, well, no, this is 1, 1, 4. It's x, 2, 4 is 4.
Oh,
It's from the homogeneous transformation.
Since we're using a while loop, we don't know how much iteration we do.
Yeah. So this one, if you're too conservative here with your error, it might take a while for it to reach that, or may never reach it. Right? So you could do, for example, have a counter, and then say do it 10 times, 100 times. We can also say, well, when this delta theta here becomes too small, we can also stop because the variation is not really improving the solution that much. Any other questions here? I find it really interesting how we can take a mathematical optimization and go straight into a robotics problem. We have everything we need already there. The Jacobian, the error, and everything is just kind of connecting two different concepts together. Yeah.
We can just extend this for joints just by changing theta and to add more joints and change the code.
Yeah.
We just,
Yep. All right. So here is the simulation. The robot is at 0, and if you look at your PDF, if you can open the PDF in the computer with Adobe, my animation doesn't work here, but if you open this later at home in Adobe directly, you'll see how the arm. Does anybody have can open it in Adobe? It took me a while to do this animation. So I want the robot to go here, position 2, 2, and each link here is 1. So the robot, the optimization will bring the robot up here and then eventually converge over there. Now, that doesn't, be very careful here because people sometimes confuse this with what the robot is doing. This is not what the robot is doing. This is you looking for solutions to bring the robot where you want. You wouldn't give the robot commands for every step of the iteration. It doesn't make sense because you know that you are far away from it. You will run this several times. Once you find your solution, then you only give that position to the robot. You see the difference?
Yeah, so in the previous slide, when we were doing the algorithm, the robot's just stationary and then it will move after the algorithm.
Yes. So this is happening offline. Right? You're not touching the robot. You're running this several times, and when you're satisfied with the solution, then you go to the robot and make it. Right, but again, if you so this is for 15 iterations, and you will see later it oscillating around the position and then eventually set. Okay, so here is the error as a function of the iteration number. I just let it run for a few times. That other one is just only 15 times. This one I ran for 4,000 times. You see a big jump in the error in the beginning, and then it gets smaller and smaller. Right? I decided to stop here. I'm happy with an error of less than 0.1, but I could keep going until the error is small. Right? How do you make this faster? Well, I could increase lambda, but be careful, because if you increase lambda too much, remember that you can now bounce back and forth between two different minima, and then you never reach the actual solution we want. So once again, the initial guess affects the final result. Wrong guess may not converge. So ideally, what it would do here is start to in a position, give points to follow that are close to one another. Wouldn't let the robot jump too much from one point to another. Would discretize that trajectory with the smaller intermediate points and then go one by one. Is it working?
Yeah.
One. There you go. Sort of.
Yeah.
Yeah.
There we go.
Anyways, it's very underwhelming. Anyways.
Yeah. It really is.
But anyways, you see that's how the robot would bounce around the point until it finds its actual position. But once again, that happens offline. Once you find a solution, then you go to the roller. So what if I want to do orientation too? Let's go back to this, and now I want the robot to position the tip and a given point, and also the elbow.
So if you define an orientation, will then the lambda size not matter because then it won't jump towards solutions?
Now it will. Mathematically, there is no difference. But instead of going with an orientation, what I could do here is to specify a third point. See, if I want this robot to go, let's say, on an angle, let's say like this, I want to place the end effector here, but I wanted to place the end effector in this orientation. What can I specify? I can specify the orientation, x and y, and I can take another point, any point, could be this point, could be that point, and say I want this point to be here. I'm choosing here to take the end of link 2 and specifying the x position. That is sufficient. I don't need to specify x and y, right? If I say that x needs to be here, there's only one possible solution that will make the robot go in that orientation. Does that make sense? I don't need to overly constrain the problem. So I'm saying now, go to the end effector here, so 2 points, x and y, same as we did before. But now my desired position has a third point, that is the x position of the second link that I get from the transformation 0 to 2, and this is the element 1 form. How does the Jacobian change? Well, now the Jacobian has one extra element, because my function has one extra variable. What's the last line there?
Derivative of like x2
Derivative of x2.
with respect to angle 1, angle 2, angle 2.
Exactly. Now this theta 2, x2 is completely arbitrary, as I said. It could have been y2, it could have been any other point along the robot arm, so long as you can get the expression for it. So here is the same simulation. Yeah.
Could you please repeat why we're getting that extra constraint?
I want the extra constraints because I want the robot to always go on a straight angle. I want it to go to this point, but I want it to go to that point following this orientation.
Also, since there's just the one solution, we know that it's straight.
Yeah. Right. So let's say each of these arms here is 1 meter long. I want the robot to go to this point, and this point is 1, 2. All right. There are several solutions for this. You could reach that in many different orientations. But if I wanted to go like this, I can say that at this point, the x of this point needs to be 0. Or I could say that the y of that point needs to be 2. Right, so if I apply any of these constraints, then that's the only possible solution for that specific orientation.
So it does depend on the final place that we want to go.
Yes. Yeah, because right, if this is one constraint, that's another constraint. So here's the solution. The purple dot there is where I want the unit vector to go, 2 constraints. And then the base here is, it would be x position at the end of link 2, that I want to be at 0. Why at 0? So that the arm goes straight, like that. Alright? You can see the utility of that in laparoscopic surgery here. And I would make sure that the robot goes in with a specific orientation. You're basically another more complicated way to specify the orientation of the robot. And then you see the result. Now you see this is not perfect. This is not perfectly aligned. Right? We have no guarantee that the cost function will reach 0. Right? So that's the compromise when you use this. We are always allowing a small error to exist. And look at the error per iteration here. It drops sharply in the beginning, and then it's slower and slower. Does that make sense? Okay, let's do one case study here. Back to that problem of percutaneous nephrotomy. Remember we discussed that before, and we ran into the very same problem. We had several mathematical constraints on the robot arm that prevented us from getting a inverse kinematics equation. We couldn't simply use academic inverse kinematics equation because we had some joint limits and other things that we had to do. So to control the robot this time, we had to do the inverse differential kinematics. What do we want to do? We want to reach point 1 through point 2. We want the robot to go to inside the kidney from passing always by point 2. So eventually point 1 will move around here, but the robot will always reach that point through P2. Now let's think about it. How can we use what we learned to control the robot in that way? I can define 2, instead of specifying the position and the orientation, I could always say, go to P1 following that specific orientation. It's easy to calculate a vector along that line. Right? But we can do that, so we know where P2 is. So can we now say there are 2 points along the tool of the robot, and I want these 2 points to be in these 2 specific positions. So one constraint is P1 is a set of 3, is a 3D point with X, Y, and Z. I know where it's supposed to go, and I know where it is on the tooltip is at the very end of the tooltip. So I could define my transfer function, my cost function, as being the distance between the tooltip and P1 first, right? But that doesn't guarantee our success here because we want to pass through P2. So what's the second constraint?
Location of P2, like the entryway.
Is the location of the distance between P2 and the corresponding P2 on the tool shaft. If we attach a tool to the robot that has a distance D, what is P2? Well, it's simply D minus the distance between P1 and P2, just along the tool shaft going back. Right? Remember on the academic for the kinematics, the last link is a prismatic joint, and the distance D along Z is 0. But if you now attach a tool, the tool here has a length D, is just that a length L, D6 will be L, right? So I can calculate the tool tip by simply plugging in L, and I can calculate the corresponding point P2 on the tool by doing L minus the distance P1 minus P2. So now I know where the tooltip is, and I know on the tool, if I want the tool to be this distance back here, I know where that point is on the tool. So I can now define my cost function as being the distance between 2 points in space, between the tooltip and P1, and between a point that is P1 minus P2 behind the tooltip and P2. Right? So I'm organizing the desired position here and the actual position as, let's calculate here, let's find the actual position x1, x2, sorry, x1, y1, z1, which is basically the Cartesian position of P1. And then concatenate here x2, y2, and z2, which is the position P2. I could put this in any order, doesn't matter. And then the desired position is what? Is x1d, y1d, z1d, x2d, y2d, z2d, which are the physical locations where I want those points to go to. What is the Jacobian? Is the partial derivatives of all of these with respect to all angles. Alright, so x1 partial derivative with theta 1, theta 2, theta 6, and so on and so on. Right, but you see now we constructed Jacobian in an interesting way, because these are two sets of three-dimensional points. And the Jacobian is calculated that way. Instead of having here the angles, remember we could have the orientation angles, right? We have another set of points. It is completely up to us to define the Jacobian that way. Also, it didn't need to go in this order. We could have put x1, x2, and then it would be v x1 theta 1. The second line here instead of x1 would be y1 would be x2.
So it doesn't matter how you put the data in the Jacobian.
Well, so long as your Jacobian is consistent with this. Right? So here is the result of the Jacobian. I'll give you some time to copy this because this is important. Now, here. Alright, so that's not the Jacobian, that's one cell of the Jacobian. Right, there are 36 of these. Alright, so final exam, one question arrive that.
Just get the full 3 hours.
Okay, so this is one cell of the Jacobian matrix having 36 of these.
What's the runtime of this?
The runtime is pretty fast. It's milliseconds to do it. It's really fast. To do it properly. So how did we calculate all this? Did we do that by hand? Of course not. Now we have better ways to do it. So I posted this two codes in MATLAB, two MATLAB codes in Brightspace that both of us will load. So the first one is to calculate the Jacobian. We don't want to do that by hand. So here is a method to do that. You can use this later. So this is exactly that up to this point here. This is exactly that code we derived in lecture 4 or 5 that we did together. Remember? It's simply the DH parameters. I'm assigning specific DH parameters that will match the robot, doing the transformation matrices, calculating them, and then from here what we do, we can extract expressions for x, y, and z. Yeah? One difference. Notice that in line 7, thetas are not given any values. They are given a symbolic variable. So when you run this, theta, all of these transformation matrices are functions of theta 1, 2, 3, and 4 as variables. Right? So you can get the expressions for the forward kinematics through that. How do you find the Jacobian? Well, take the partial derivative with respect to theta 1 of the end factor x. End factor x partial derivative with respect to theta 2. End factor x partial derivative with respect to theta 3. And so on. Second line, same story, but now is, where is the second line? Is C32. So now this is x. Right? Y. Y with respect to theta 1, y with respect to theta 2, and so on, and we keep going. And then when you run this, you have now an expression of a matrix that is already built, and you can get the, this is the Jacobian. See, as a function of all thetas and everything.